Hello everybody. As promised, I am going to record the last lecture number 4 on sustainable energy harvesting using mechanical vibrations. Mainly, we will be dealing with piezo, pyro, and tribo effects in this lecture. The overview of the presentation include mainly the energy harvesting sources. This one I explained you already in the class. Because this is the time that the energy harvesting domain has been generating great interest among researchers, scientists, and everybody in the field of industry and so on. The energy harvesting actually is the process of extracting very small amount of energy from various resources, and this can be mechanical energy harvesting or photovoltaic effect, like the last time we discussed in the case of solar power. In all the cases, whether it is mechanical vibrations or the solar energy, the energy will be converted into electricity, and this is called energy harvesting. The energy available for harvesting application is mainly it can be provided by the light, so as in the form of solar radiations, and sometimes it will be in the form of radio frequency and also the thermal and mechanical energy. Then the various materials or the various devices that can power due to this electrical voltage can be from battery recharge or maybe the self-powering devices. The scope of the energy harvesting resource is in the efficiency of the harvesting methodology and also the efficiency of the energy conversion process. Yeah, as you can see in the overview slide, the energy harvesting resources can be of different kinds, such as biochemical reactions. I am sure that everybody is well aware of the biofuel cells, enzymatic and microbial fuel cells. You already submitted an assignment based on this. And another one is thermal energy. Thermal energy can be mainly in two types: thermoelectric and pyroelectric, which we will cover in after a few slides. We will be covering this one. And biomechanical energy, it can be piezoelectric, triboelectric, electromagnetic, electrostatic effect, and the reverse electrowetting process, and the solar energy which was covered, and biochemical reactions including biofuel cells was given as the assignment. And in today's presentation in this presentation we will be covering the biomechanical energy as in the form of piezo, tribo effects, and the thermal energy, thermoelectric and pyroelectric effect. Yeah, if I go a little deeper, energy harvesting can be divided into kinetic, electromagnetic, thermal, and thermal energy harvesting. Finally, moving to the application part. And in the case of kinetic energy harvesting, actually for medium and large scale harvesting, the techniques such as solar, wind, hydro, geothermal, etc. are used. Solar energy harvesting is one of the most practical applications because of the highest energy density compared to other sources, and also the availability of the raw material, the efficiency, and also the wide varieties of materials that can be used for energy fixation and so on. Due to the fact that the vibration sources are unique in the ambient environment, vibration based energy harvesting is one of the attractive solutions as well. As in the case of direct human action from walking or body movements, wrist movement, shoulder movement, and this kind of it's really interesting to see this kind of mechanical vibrations to convert into electricity. And basically the vibration to electricity conversion mechanism can be implemented by piezoelectric effect, electromagnetic interactions, electrostatic, and magnetostrictive transducers. Out of this, the piezoelectric transducers are being widely investigated because of their high efficiency and the common nature of the vibrations. Then kinetic energy harvesting is mainly based on the acceleration of some kind of mass. For example, if you have some movement, some base movements, a vibration is set up in the mass spring system. Yeah, in the case of a mass spring system, the mass is being moved, or the vibration of the spring can move the mass attached to the spring. This kind of movement can be generated, can be kinetically monitored and kinetically converted this energy to electrical energy. On the other hand, the piezoelectric energy harvesting, it is based on the MEMS system, micro electromechanical systems, with a few of movable components. Additionally, the energy harvesting is creating electrical power. It can be based on generally in the form of any kind of movement. Okay. So it can be the electrostatic influence or the radio frequency, such as in the case of radio frequency power in the form of electromagnetic waves from the environment. So the radio frequency is used for communication and communication of radio signals, and these signals can be effectively converted to electrical voltage as well. Also there is another possibility, that is thermal energy. The thermal energy can be thermoelectric effect or pyroelectric effect, which I already discussed in the first slide. Also, we will be covering more on this topic in the later stage. If we go to a little bit more details about the slide number 4, we can also see that the pyroelectric, piezoelectric, triboelectric, photovoltaic, thermoelectric, flexoelectric, all these energy harvesting systems comes from the electrochemical processes controlled by energy harvesting. So you just need a particular material applicable for a particular effect like piezo or pyro or photo or tribo, and this material can convert the particular energy related to the mechanical vibrations to energy harvesting. For example, in the case of piezoelectric, there can be a typical material, and this material will undergo some kind of chemical reactions within while it is being vibrated or while it is being mechanically deformed. These movement happening inside the material will be able to convert to the electrical voltage. This is happening in the case of pyroelectric effect also, but all the pyroelectric transformations, energy harvesting, is associated with a change in temperature which is marked by delta T. And the photovoltaic we already discussed, and the thermoelectric and pyroelectric both are similar. There are a few differences between only a very nominal difference between pyro and thermoelectric materials, which we will be covering in the subsequent slides. And the flexoelectricity is also related to the piezoelectricity. Both are related because both work on the bending or the mechanical deformation and the conversion of the mechanical deformation to electrical voltage. And the tribo is always related to the contact electrification process, or it is the frictional force or rubbing between the two surfaces. This surface rubbing or surface interactions can create electrostatic interactions between the materials and can produce electrical voltage. Yeah, so moving to the one of the main important topic suggested in this presentation, which is piezoelectricity. The motivation of piezoelectricity, I already explained in the class what is the real motivation of piezoelectricity. There are renewable energy resources such as solar and wind power. As you can see in the picture, there are two houses, both are depending upon the renewable energy resources. But what will happen if the climatic conditions is not feasible? If there is rainy season without any sunlight and without any wind, then the powering the house with the renewable energy resources becomes questionable. In that case, you don't need to worry about the powering the whole home. You just need to dance inside. This is the significance of piezoelectricity. So as long as there is physical activity, piezoelectricity could generate power. The next slide shows the various applicability of the piezoelectric materials. Piezoelectric material is nothing but the conversion of mechanical to electrical energy, and this can be used for breathing, blood flow and heart beating conversion, breathing conversion, and it can be used in biomedical field, such as in the form of implantable devices, self-powering devices, wireless sensors, nanorobots, nanosensors, MEMS. and so on. This is the general slide which shows the various applicabilities of this kind of material. And the next slide, which is slide number 7, is a video, and I request all of you to go through this video to know more about the piezoelectricity and piezoelectric material. The video will explain what kind of piezoelectric material that we are normally using and the mechanism within the piezoelectric material. In a typical piezoelectric effect, there are two kinds of phenomenon, which is direct and converse piezoelectric effect. The direct piezoelectric effect, which is a sensor mode of operation. So in this, you will be giving some external outputs, like in the form of mechanical vibrations, or we will be giving some kind of inputs in the form of external stimulus to a particular material, and the material will respond in terms of voltage differences or resistance differences or capacitance differences. This is normally the sensor mode of operation. In a sensing, if you have a sensor in your hand, say for example pressure sensing, you will be giving a pressure to the material, and the material will be sensing the pressure based on the electrical voltage variations or resistance variations, some parameter variation. This is called sensor mode of operation or direct piezoelectric effect. You will be giving a force in the form of mechanical vibrations, and the material will be giving out, the output will be the potential difference or electrical voltage difference. The same thing can be reversed in the converse piezoelectric effect, as you have a material with your in your hand, and then you are connecting it to an electrical voltage difference. You are not going to give any kind of forces into the material, but instead you will be connecting it to an electric socket, or you will be connecting it to an external electrical voltage. Then what will happen with the electrical voltage? The material, the input here is the electrical potential difference. The material will take the electrical voltage, and with the help of the electrical voltage, the material starts vibrating. So it will start the movement, which is called the actuator mode of operation. This is the principle of an actuator. An actuator is nothing but you have some material, an actuator in your hand, and then you are connecting it to an electrical power source. Then the material will vibrate, or the material will move, the device will move. This is the actuator mode of operation, or which is also called the converse piezoelectric effect. Now the question is how a typical piezoelectric material can work. I'm sure that you learned the principle of a piezoelectric material from the video, which was in slide number 7. But now, say you have a class, you have some materials with well aligned dipoles within. Like, say for example, you have a crystal piece or a ceramic piece with so many dipoles within, but these all dipole is nothing but a positive and negative club, like charged units. So if all these charged units are in perfectly aligned situation, then if you are giving a disturbance to such a system, the change will be more visible, isn't it? Like if all the dipoles are in perfectly aligned position, then you are giving a mechanical deformation or mechanical vibration or a hit or a press or some kind of mechanical force you are giving on the material. Then what will happen to the perfectly aligned or perfectly positioned dipoles in the material? It will be disturbed. So actually this disturbance, while giving a mechanical force to the perfectly aligned system of dipoles in a material, the disturbance created will be responsible for the piezoelectric effect. But the problem is, in a natural ceramic material or in a natural piezoelectric material, the dipoles will not be aligned all the time. The dipoles will be randomly oriented. Instead of aligning it in perfect position, all the dipoles will be randomly oriented. So what we will do for a randomly oriented system, if the class itself is disturbed, or if the students are here and there in a typical class, or if the dipoles are here and there they are not aligned perfectly, and you are disturbing the system, the change will not be that much visible, right? But this is the different case, like when all the dipoles are in perfect alignment. So the challenge behind a piezoelectric material is you have to convert the randomly oriented dipoles in a material to perfectly oriented dipoles before testing the piezoelectricity, and this process is called polling. This is normally done like whenever you have a piezoelectric material, you will do the polling by giving a very high amount of electrical voltage in the beginning. You will be connecting the material to an electrical potential difference, and you will give a jerk, or you will give a very high potential to the system, so that all the dipoles will get aligned. Then you are proceeding to test the piezoelectricity. Give some mechanical vibrations, pull, push, or compression, or extension, or elongation, or so any kind of mechanical activity, and then you will be measuring the electrical potential difference associated. So this particular process which is done in the beginning is called the polling. And normally there are different ways of polling, and the first way is giving a huge potential in the beginning, which is also called as corona polling. Normally for polymers like PVDF is a piezoelectric polymer. For this kind of polymers, we will not do the corona. We can do the corona polling also, but we can also do another process which is called electrospinning. Electrospinning is nothing but you will get a polymer solution in a syringe, and then you will do the spinning by connecting it with a potential difference again. So during electrospinning, your polymer is in the form of a solution. Then the solution will be pumped through a needle, and this needle will be connected to a very high potential difference. So in the presence of this very high amount of potential, these polymer solution will be converted to fibers. So finally, the product that you are getting will be like a tissue paper, which is a electrospun polymer fibers. We have an electrospinning unit in CAM. So when this electrospinning is done, you don't need to do any additional polling, because electrospinning itself is connected with the high potential difference, high electric voltage. So the alignment of the dipole will happen additional, like an additional process during electrospinning. So you don't need to do the polling again. Yeah, that's why whenever you are going to the literature about electrospun nanocomposites for piezoelectric energy harvesting, or polymer nanocomposites or polymeric materials for piezoelectric applications, then you will be seeing a lot of papers on electrospinning. This is because electrospinning will discard the necessity of additional polling required. So this is an easy process for generating piezoelectric materials, piezoelectric polymers typically. So when we go to the piezoelectric materials, Rochelle salt was the first material discovered to exhibit piezoelectricity. This one I already talked about this in the class, because it is a ceramic material, and later crystals such as quartz, cane sugar, Rochelle salt, all these materials were found to be piezoelectrically active. And another materials which is ceramic, lead zirconate titanate, barium titanate, these materials were also identified to be piezoelectric. And also polymers such as polyvinylidene fluoride, which is a semi-crystalline polymer. And you can also see that the center of symmetry, how the center of symmetry for positive charge and center of symmetry for the negative charge changes in a compressed crystal. And the typical necessity of a piezoelectric material is the absence of a center of symmetry. Whenever there is no center of symmetry, and whenever there is a mechanical deformation, definitely the symmetric alignment will vary, and this difference in alignment is responsible for the piezoelectric output voltage. And if I move to the slide number 12, you can also see this effect in a very noticeable way, which is a perovskite PZT lead zirconium titanate unit cell, and there are two images. First one is the PZT unit cell in the symmetric cubic state, and another one is tetragonally distorted unit cell below the Curie temperature. Actually, the Curie temperature is a temperature at which the magnetic properties of a typical material varies above and below the temperature. So when this PZT is considered at a particular temperature above which the material will be a symmetrical cube-like structure, and after that when the temperature is cooled down, when the material is cooled down, it is distorted to tetragonally distorted unit cell. So this shows that how the material's center of symmetry can be affected with the temperature variations, and also such kind of materials, how it can be effective for piezoelectric energy harvesting. The next slide is a very important slide because it discusses some mathematical equations and a formula for piezoelectric constant. What is a piezoelectric constant? Normally, the piezoelectric charge coefficient relates the electrical charge generated per unit area with an applied mechanical force and is expressed in the unit of coulomb per Newton. Because coulomb is the charge, coulomb will give you the charge generated in a typical piezoelectric material, and also the Newton will give you the strength of the mechanical force that it is being acted to generate that charge. So the charge is being generated with a typical mechanical force, and this will, whenever there is a the charge generation with an applied force, it will create a strain inside the material. So the constant, a typical constant can be associated, which is a ratio of the strain developed within the material and the applied field to the material. And this constant can be associated with some other parameters, which is known as the dielectric constant of the material, the elastic compliance of the material at a constant electrical field, and also electromechanical coupling coefficient. So it is useful, it's very important to know that the large D constants relate to large mechanical displacements, which are usually sought in motional transducer devices. Conversely, the coefficient may be viewed as relating the charge collected on the electrodes to the applied mechanical stress. And this constant, the charge generated to the applied mechanical stress is always depending upon the direction. You can see that the 3-3 mode and 3-1 mode, it measures in which direction the stress is being applied. So in the first case, you can see that the force is acting in the 3 direction. The force is acting in the 3 direction. It is a downward force, and the voltage is forming also in the same direction, right? But in the case of 3-1 force, it is not a compression way of movement, but it is an extension way of movement. But still, the energy is being, or the voltage is being generated in the third direction. So in both cases, the energy is being generated, the voltage is being generated in the 3 direction 3 x, y, z direction. But in the first case, the force is in the third direction, the compression mode, but in the second case, the force is in the first direction. That's why 3-3 mode and 3-1 mode. And when this 3-3 mode operates, for example, the coefficient, the piezoelectric coefficient is calculated based on the force applied and the voltage generated, both are in the Z direction, then we call that piezoelectric coefficient as D33 constant. And the matrix shows how to calculate the D33 constant. The matrix is not so important, but the value of D, the equation of D is very important, and also the demonstration of the 3-3 mode and 3-1 mode is important. So if I ask what is D33 constant, you have to demonstrate it and you have to explain it with the equation. The next slide in fact shows what is a piezoelectric or pyroelectric or a dielectric. All these things are related or not. So the relationship among dielectric, piezoelectric, pyroelectric and ferroelectric materials is given here. Normally, most high-performance piezoelectric materials are also ferroelectric materials. So another question is, what is ferroelectricity? It is a character of certain materials that have a spontaneous electric polarization that can be reversed by the application of an external electric field. And also dielectrics are the big family, with the core subset being ferroelectrics, because dielectric materials are basically electrical insulators which become polarized by the peripheral application of electrical field when placed across the plates of a capacitor. Piezoelectric materials belong to the dielectric group, but a stress can create a net separation of positive and negative charge in a piezoelectric crystal that has a non-center of symmetric crystal structure. Pyroelectrics are those materials with the ability to generate a temporary voltage when they are heated or cooled, since the polarization magnitude in a pyroelectric crystal can be thermally changed by the temperature change. So by comparison, for a piezoelectric crystal, it is the mechanical stimuli resulting in the polarization change, and as a consequence, charge is built up at its surface. Ferroelectrics are an experimental subset of pyroelectric materials. So this means all ferroelectric materials are pyroelectrics and all pyroelectric materials are piezoelectric. However, not all piezoelectric materials are pyroelectric and not all pyroelectrics are ferroelectric. So it means the crystal symmetry governs the categorization. So if I explain it in more detail, a ferroelectric materials is a material that exhibit ferroelectricity, and ferroelectricity is the ability of the material to have spontaneous electric polarization, and the polarization will be reversed by the application of an external electrical field. So when the external electrical field, application of the external electrical field is in the opposite direction, the polarization can be switched also. It will be from positive to negative and negative to positive, depending upon the direction of the external electrical field. Then this reversal of polarity of a ferroelectric material by the application of an external electrical field can be called switching. The ferroelectric materials can maintain the polarization even once the electrical field is removed. And such materials have some similarities over ferromagnetic materials, which reveal permanent magnetic moment. And the hysteresis loop produced for the ferromagnetic material and ferroelectric material both will be the same. And since there are similarities, the prefix is the same. That's why ferro and ferro both are ferroelectric and ferromagnetic. So when we compare the ferroelectric material with a dielectric material in terms of the polarization and hysteresis loop, just for example, take the dielectric material and a peripheral electrical field. We can see that the polarization will always be directly proportional to the applied field. That's why when the polarization enhances or when the applied field enhances, the polarization is also increasing. This is very clear in the case of dielectric polarization or dielectric material. And next, when we polarize a paraelectric material, we get a non-linear polarization. That's why it is in the form of an Z shape. However, it is a function of the field, but still it is a function of the field, but we get non-linear polarization. Then we take a ferroelectric material, and it is also showing a non-linear polarization in the case of ferroelectric material, the last one, which will show a cyclic graph. In the case of piezo and pyro and dielectric, both the three are in the same way. Only the difference is what is the external field which is being applied to. For dielectric materials, it is the external electricity, and for piezoelectric materials, it is the external stress, and for pyroelectricity, it is the external temperature. And in the case of ferroelectric material, it is similar to a C CV curve or cyclic voltammetric curve, or it's going and coming back. Reversible switching can be seen in the case of piezoelectric materials. A particular hysteresis loop is being evident. And the properties of these materials exist only below a definite phase conversion temperature, and above this temperature the material will become paraelectric, and this temperature is always called the Curie temperature. This is the temperature above and below which the typical properties of a material will change. That's why it is called Curie temperature. Most of these materials above TC, the Curie temperature, will lose the piezoelectric property. Slide number 16 and 17 are both important. All are important. The shape of the curves are important. Dielectric, how dielectric or para or piezo or pyro or ferroelectric materials vary. And slide number 18 also shows what is the relationship between piezo, pyro and thermoelasticity. So when we come to the pyroelectric materials, it is a material that undergoes a change in polarization as the temperature of the system is varied. This effect can be utilized for applications ranging from thermal imaging and sensing to waste heat energy conversion to thermally driven electron emissions. And the figure which is given on the slide number 18 will show you, it's showing a Heckman diagram depicting the various thermodynamic, coupled, electrical, mechanical and thermal susceptibilities of crystal materials. So when we are going through this diagram, the physical understanding of the pyroelectric effect is very clear. Pyroelectricity can be defined as the variation of spontaneous polarization as a function of temperature. Both are evidenced. Both can be seen as E and P, which is in the diagram. So spontaneous polarization is denoted by the letter P, and the temperature is denoted by the letter T, and the electrical field, which is E, and the stress is X. So by carefully modulating or carefully understanding these parameters, we can find out that the stress variation which will lead to the E in the case of piezoelectricity, that voltage generation, and for the pyroelectricity, E and T are connected. Temperature variation is giving you the E. And also there is a red arrow, pyroelectric effect. Temperature variations will create the polarization, and from polarization the electrical voltage is also related. And the thermoelectricity can also be related by using the same diagram, as the stress value can be produced by the temperature variations. So this is the relationship between the thermoelasticity or thermoelectrical effect with the pyroelectric effect. In the same slide, the pyroelectric, a typical pyroelectric nanogenerator is given, and also the variable pressure sensor along with the pyro breathing sensor. The heat energy produced after the breath, during the exhaled air, is being converted to electrical energy, or it's being recorded in the form of sensor signals that can also be seen from the same slide. And the next slide shows the difference between a typical piezoelectric material, pyroelectric material and ferroelectric material. Just go through this. You can also see what is the definition, then the basis, the different kinds of materials being used, and the applications for these three effects. Slide number 20 again shows the mechanism of pyroelectricity. Whenever there is a dt by dt, which is the temperature change with respect to time. The capital T is the temperature variations and small t is the time variation. So whenever there is a temperature change with time, in the first case there is no change in temperature with respect to time, and in the second case the temperature variations with respect to time is greater greater than 0, which is the heating, and another case, the third case, is dt by dt less than 0, which is the cooling. So in all three cases we can see that in the first case there is no temperature variations and the system is like very normal, that there is no power or there is no current flow in the system. It's very stable system. But in the case of heating and cooling, you can see the IP, there is a power variation, the power is being changed, or the electrons is flowing in the first case, and in the second case also the electrons is flowing, but in the opposite direction. So this will show the difference between a typical heating process and a cooling process, and how exactly the temperature variations can result in the charge generation and charge movement, which is the mechanism of pyroelectricity. The pyroelectric effect is a change in surface charge or the capacitance in response to a change in temperature. Pyroelectric materials are usually crystalline materials and are coated with a black absorbing material. The thermal mass of these devices has to be kept very small. Since it is a change in temperature which generates the current, the incident radiation must be chopped. However, the response times of pyroelectric detectors are much higher than for thermocouples or thermopiles. Also, the pyroelectric effect describes a temporary voltage generated by certain materials when the temperature applied on the material is changed with respect to time. It is different from the thermoelectric effect, where the temperature gradient is varied in the space instead of the time. Now moving to the last part of this lecture, which is the triboelectricity, slide number 22. We can see that how the triboelectricity can generate power, which is the comb and dry hair in effect. So if you have a comb which is very clean and very dry, and your hair is also very clean and dry without any dirt or without any oil particles on the hair, when you rub the comb with your hair, your comb will get some power. Like after combing your hair, your comb will have the ability to attract a small piece of papers or small lighter pieces of thermocoals or something related. And also this is the cat fur effect. Sometimes you can see that the cat fur can attract the thermocol pieces. So this is called contact electrification or the triboelectric effect. And in the original case, it is tribo-negative and tribo-positive, two subsequent layers of a system. One will be act as negative and one will be positive, but there is no external influence. So it's very stable system. But when you press and release, these surfaces will be influenced, and charge regeneration or charge orientation or charge movement can happen within the surface. So when you rub the surface, when you press the surface and release, these charges can be generated on both sides, or the upper plate and lower plate of the same material, and this is responsible for the triboelectric power generation. The mechanism is based on the spontaneous generation of electrostatic charge when two chemically different materials come into contact. The tribo-negative material accepts electrons with the tribo-positive, while the tribo-positive material donates. The separation of the two materials induces an electric current in an external circuit, which can be used to power appliances. While TENGs produce sustainable energy, the TENGs themselves are generally not made from sustainable, which is renewable materials. This is again another problem. Normally everybody will talk about sustainable materials, and the TE energy is a sustainable source of energy, but actually the triboelectric materials are not always made of sustainable materials. Nowadays the fully biodegradable triboelectric energy generators are also there. So such kind of materials we will target with the biopolymers. Remember, polylactic acid, polyvinyl alcohol, these biopolymers are also targeted for creating triboelectric materials. Porous materials can also target triboelectric power generation, because the reason is that pores at and close to the surface increase the areas of charge to build up. This can load more and more electrostatic charges within, and it can create higher external electrical circuits. And slide number 24 and 25 again detailed, it shows the turboelectric power generation mechanism in detail. In the first case, 24, slide number 24, the turboelectric nano generator, TENG, turboelectric nano generator, is made on a PTFE and cotton with a typical substrate and conductive material. So it's just like rubbing. For rubbing, it's not like taking two materials together and rub, but the materials should be properly embedded or properly protected in some other kind of materials like PTFE or PDMS. It will be protected, and a typical nano generator will be made, and this nano generator will be rubbed together, or it will be electrically contacted together to produce electrical charges. Again, slide number 25, which also shows the mechanism of turboelectric power generation. There will be an upper electrode layer and a lower electrode layer with a dielectric layer or a polymeric layer in between. When you rub or when you compress or when you move this piston, then power will be generated by the contact electrification process. So by this, I'm ending this lecture, and there can be some possible questions from this section. Is the definition like dielectric? What is dielectric? What is ferroelectric? Or can you explain the graph of the electrical voltage E versus P graphs for the piezoelectric and the dielectric or the ferroelectric? So the definition itself is very important, and also the theory and mechanism of piezo, pyro, and turbo, which is very important also. Another important question that can be asked is D33 constant, its equation, and or maybe the representation of D33 constant. And I expect your questions by WhatsApp or by email before the exam. And I wish you all the best, and all the best for this module. And I expect everybody will excel in their exams. Thank you so much.